In this video, we're going to talk more about future value and do an example that's a bit more realistic to the real world. So to start, I have stated at the top of the screen the formula for the future value of an ordinary annuity, where FV stands for the future value, PMT stands for a regular periodic payment, I is the interest rate per period, and N is the total number of compounding periods. Notice that I've given the little mini formulas for I or N in case we are not given those values specifically in our exercise, in our example. And as a few things to keep in mind, that's one of the first things that I have here. If we're not given the values for I and N in the example, we're going to need to use those mini formulas to calculate those values, and we're going to see that in our example today so that you can see how that looks. We will be careful to follow the order of operations as we're simplifying. We will use our calculator to compute with exponents, and we will wait until our very final answer to round any decimals. This is to help ensure that we get the most accurate final answer possible. Alright, so let's move on to our example. Our example reads, suppose a local bank offers an annuity that pays 4.8% compounded monthly. If $2,205 is deposited into the annuity every month, how much will be in the account after 6 years? And we also want to find how much of the amount is interest. So let's take a second and write down what we know, what the information is that we are given. So we're dealing with an annuity that pays 4.8% compounded monthly. So this is actually an annual rate, and so that means that R equals 4.8%. As a decimal, that is 0.048. So remember, when we utilize the rate as a percent, we need to be sure to change it into a decimal first. We're also told that the money is compounded monthly. The variable that stands for the number of times the money is compounded is M, and when we compound monthly, that means it's being compounded 12 times a year. So M is 12. We are making payments of $2,205 every month, so that means that the payment is $2,205. And we want to know how much will be in the account after 6 years. That means we're after a future value. That's what we want to find. And the time in years is 6. So now that we have all of the information stated that we're given to find this future value, I'm going to go ahead and write down the future value formula. And we can begin to plug in the values that we know into the formula. So if the future value is what we're trying to find, the payment is $2,205. Then we have 1 plus I. Now we are not given I in our problem, so we need to use that mini calculation to find it. So recall back up here in our introduction, I is the interest rate per period. To calculate I when we're not given that value, we need to take the rate and divide it by the number of times the money is compounded per year. So we're going to take the rate and divide it by M in this case. So coming back down to our example, I equals R over M, which in this case is 0.048. The number of times that our money is compounded per year is 12. And when we divide 0.048 by 12 in our calculator, we get 0.004. So instead of I, we're going to replace I with 0.004. Now, as far as n goes, again, we're not given n in our original problem, so we need to do a mini calculation. Just to refresh your memory, n is the total number of compounding periods, and to find that, we just need to multiply the number of times the money is compounded per year by the number of years. So coming back down to our problem, n equals the number of times the money is compounded per year times the number of years. In this case, it's compounded 12 times a year, and it's going to be for 6 years. So 12 times 6 is equal to 72. So instead of writing n, we're going to write 72. And then continuing on with our formula, we subtract 1 from the numerator and divide by I. Again, we're going to use 0.004 for that value of I. Now that we've substituted all of the values into our formula except for 1, the future value, we can simplify this right-hand side to find the future value in this case. We just want to be sure to follow the order of operations. So notice that in our right-hand side here, we have two sets of grouping symbols. We have brackets and we have the parentheses. So we're going to start with the innermost set of grouping symbols and add 1 plus 0.004. We're going to do that first. And I'm going to rewrite everything else, working one step at a time here, in parentheses 1.004 to the 72 power. Rewrite everything else so I don't make any kind of silly mistake. Now I'm going to continue with the order of operations and simplify what's in these brackets. And within the brackets, we want to follow the order of operations, which means we want to simplify this exponent term first. And I want to emphasize that we need to use our calculator to do that. So you should have an exponent feature on your calculator to calculate 1.004 to the 72 power. And when you do that, I'm going to rewrite everything else here. You should get 1.332991322 minus 1 divided by 0.004. Now I will simplify the numerator here by subtracting 1 from the decimal, which gives me 0.332991322, and in the denominator we divide by 0.004. I'm going to give myself a tiny bit more room here. Now we can divide that decimal that we just wrote by 0.004, and that gives us 83.24783.062. To find the future value now, all we need to do is multiply that decimal by 2,205. Punching that into our calculator, get a dollar amount of $183,561.47. So since it's a dollar amount, I'm writing it as a dollar amount, and I'm rounding to the nearest cent here. So now we have figured out the future value of this ordinary annuity given the parameters in the original problem. There was one other question though that was asked of us. Now that we have found the future value, it's asking how much of this amount is interest. To determine the answer to that question, so how much is interest? We know the amount of money including interest. To determine the amount of money without interest, we simply multiply the raw numbers together. So in the original problem, the deposits were in the amount of $2,205 per month. That was deposited 12 times a month for 6 years. So the amount of money that was put into the annuity without interest can be found by multiplying these numbers together. So again, $2,205, 12 times a month for 6 years, gives us a raw dollar amount of $158,760. To find the amount of money in this case that was interest, we subtract $183,561, and we'll just round this to the nearest whole number for the purposes of this part of the question. We're going to subtract that dollar amount. We're going to subtract $158,760 from that dollar amount, and the answer that we get is $24,801. So that is the amount of interest in this case, which we found by calculating the amount of money that was put into the account, not including interest, and then subtracting that from the amount of money that we found to be the future value of this annuity.